Hello, my name is Etienne Robein. I'm a freelance consultant in geophysics. My activity after careers major oil companies to deliver courses and training sessions on the seismic methods and especially on seismic processing and time and depth imaging technology. May I mention that I published 2 textbooks with the EAGE publications on velocity and reflection seismics and on seismic imaging. The title of my lecture today is on the use of epsilon and delta in anisotropic velocity model building and depth migration. Everyone knows that an accurate estimate of the velocity at which waves propagate in the subsurface is fundamental in pre-stack depth migration projects. To get this velocity field is the objective of anisotropic velocity model building. It's now unanimously recognized that the subsurface is not only heterogeneous, i.e. waves propagate at different velocity at different locations, but also anisotropic. Propagation velocity is a function of propagation direction. If we neglect anisotropy in seismic imaging in depths, we still generally get sharp images. These images, however, are not accurate in the sense that reflections are not at the correct depths, neither at the correct lateral position. Let me take this example to illustrate this point from Schlumberger and Sonangol, courtesy of Olga Straveva. This is an example of the image where we neglect anisotropy, and that's an example where we account for anisotropy. In this case, you get a nice image, but as the author says, it's enough to identify target, but if you want to successfully drill, accurately locate your wells, you need to account for anisotropy. We discuss here why this is the case and how we can account for the presence of anisotropy using the famous Thompson's parameters epsilon and delta. And we will see that borehole calibration is necessary to achieve this goal. The lecture is organized as follows. Firstly, I relate anisotropy to layering in the subsurface. Secondly, I briefly present again Thompson's epsilon and delta parameters for VTI and TTI models. Next, I use a synthetic example to investigate the impact of epsilon and delta on depth imaging, to deduce finally a classical strategy, amongst many other possible, to estimate these parameters, once again using borehole information. Rock physicists told us that velocity in the subsurface depends on the local elastic properties, and for P waves, for instance, most precisely on the so-called uniaxial compression models. And these parameters vary. This is what we call heterogeneity. Just to give an idea of how we deal with heterogeneity in our models, I superimpose on this outcrop the grid that we would use in a velocity model update. We assign one velocity value at each point of this grid. And of course, we have these values varying spatially. So this is for heterogeneity. Now let's talk a bit about anisotropy. Looking at this outcrop again, let's propagate the wave vertically, and we may define a vertical velocity. Let's propagate the waves horizontally, we could define a horizontal velocity. What I'm claiming here is that horizontal velocity is greater than vertical velocity. Let's discuss this point. Let's take a kind of thought experiment in a rock physics labs. We take this huge piece of rock, the size of the seismic wavelength, say, and do these rock physics experiments to try and measure the uniaxial parameter. Do the same experiments horizontally again, and let's call the parameter we would get M horizontal. We derive from this kind of thought experiment that rock compressibility is not the same vertically and horizontally because of bedding. Soft rocks take the burden vertically, and hard rocks take the burden horizontally. Of course, if we would do the experiments at different angles, we would get different values again. So basically, what I'm driving from that is that M is a function of direction, and since V is a function of M, V is a function of direction. So you see the importance of bedding when anisotropy is concerned. And we can define an axis of symmetry here, vertical, normal to bedding. Some people say, well, anisotropy comes mainly for shales. Of course, shales are highly anisotropic. We call them intrinsically anisotropic because they are at a totally different scale than seismic scale. But basically what I'm saying here that anisotropy at seismic scale include the overall effect of layering and the possible presence of intrinsic anisotropy in some layers. One more characteristic is that rock properties are assumed to be invariant about an axis of symmetry. This is what we call transverse isotropy. And if the axis of symmetry is vertical, this is what we call vertical transverse isotropy, or VTI, or the VTI model. So we need to describe this anisotropy into our models. So for each cell, basically the industry went to selecting Thompson's parameters for that purpose. Thompson's published these parameters in his famous paper in 1986. So the three parameters we select is the vertical velocity, velocity along the axis of symmetry, epsilon and delta. Once the three parameters have been defined in one given cell, we can compute the velocity vertical, this is one of the definition. We can compute the horizontal velocity, which is basically v vert times 1 plus epsilon, and we see a first physical definition of epsilon. And if we have a wave propagating along the ray here at a given directions, Thompsons Equations give us the value of the velocity, more precisely phase velocity, along that direction. Okay? I'm talking about phase velocity here. I have no time in the frame of these presentations to discuss the difference between phase and group velocities. Now for a given cell, we have defined v vert, the axis of symmetry, epsilon and delta. But if we look at the outcrop again, in a complex geology, we see that if we accept the concept that anisotropy comes from bedding, this model doesn't make geological sense. We have to tilt the axis of symmetry, and that's the famous TTI model, or tilted transverse isotropy model. Basically, we say the axis of symmetry should follow the layers, dips and azimuths in a 3D sense, which is not shown with this cartoon here. So in the TTI case, we have similar equations to give out the velocity as a function of directions. The only thing is you have to be careful to take the angle with respect to the axis of symmetry direction, as shown here. Alternatively, classical parameterization is the v vert, v horizontal as already introduced, and the vNMO, which is v vert square root 1 plus 2 delta, an equation we'll see in a moment again. Okay, so now that we have defined v vert, epsilon and delta, let's see how they influence the velocity as a function of directions of propagation. So instead of using equations, let's use curves. On the right side of these slides, you see the curve of v as a function of the propagation angle for v vertical, 2000 meters per second, epsilon 15%, and delta 5%. And you see on the left of the curve the value of the velocity for vertical propagation, the value of the velocity for horizontal propagations. You see again this equation that the horizontal velocity is 1 plus epsilon v vertical. That tells us that epsilon characterizes basically the ratio between velocity, hence rock compressibility along bedding, and velocity or rock compressibility across bedding. Okay, we can infer from that that epsilon is always assumed to be positive because globally rocks are less compressible along bedding. Now we can consider, for instance, propagation at 30 degrees, like this on the cartoon on the left, and that would be the curve would give us the value for that specific, the value of phase velocity for that specific angle. So we can say that velocity regularly increases with propagation angle and epsilon. That would be the curve for epsilon equals 5%, and that would be the curve for epsilon 10%. Now let's concentrate on delta, and delta only. Note, by the way, that if epsilon is always positive, delta may be negative. So that would be the curve for delta equals minus 10%, and that would be the curve for delta equals plus 15%. And you see from this curve that delta doesn't influence the velocity for vertical and horizontal velocities, and is mainly affecting velocities around 45 degrees. Okay, Thompson's equations tells us that epsilon and delta effects add together. For instance here, looking at what's happening at 45 degrees propagation, we see from the equations that epsilon and delta would have the same phase velocity for that specific angle of 45 degrees. So it's probably time now to discuss the effects of anisotropy on pre-stack depth migration, and more specifically, what happens when we neglect them. For that, I use this example, which is not really fresh, but I still like to use it because it's one of the first examples of the improvement achieved with pre-stack depth migrations, again, time processing, in the North Sea, in complex structures in the North Sea. So the image was really improved compared to time processing, as I said, but when they tied a well, they noted a depth error or depth mistie of 300 meters. At the time, anisotropy was not accepted as a concept in the North Sea. So although it was not really accepted at this time that anisotropy was important in the North Sea, the authors there tried VTI anisotropy pre-stack depth migration and got this result. As good an image, but now with good well time. You may say, well, probably the gases, so-called common unit gases, were not flat. Well, they were flat in both isotropic case and anisotropic case. The only difference is the depths. So let's investigate a bit further how would they achieve these results. Let's use a synthetic example. So this is the model I'm going to use now. On the left, with the first layer being homogeneous isotropic and the second layer being vertically heterogeneous and anisotropic with 15% of epsilon, and 5% of delta. On the right, a kinematically derived shot record with the three kinematically derived shot record. I just highlight here two locally consistent events which I'm going to beam migrate with different velocities using some kind of fast beam migration technology. And these are where the 24 shots are. Just like in the real example that I showed earlier, let's do the isotropy test first. So we assume isotropy in the second layer, and we are going to scan the vertical velocity with epsilon delta being fixed to 0. Okay, so what we'll consider here are the common image gathers at two locations, one over the flat horizon and one over the dipping horizon, the fault plane, if you wish. Let's start with the true vertical velocity. This is the common image gather we would get on the flat horizon, and that's the one we would get on the dipping horizon. Let's investigate a bit further that. We see that for the so-called near offset, like illustrated by these rays, we get the right migration. This shouldn't be a surprise, since the rays sense basically velocity which are almost not influenced by anisotropy. But when we look at large offset, long offsets, we see that the rays saw high influence of anisotropy, and we don't compensate for that with vertical velocity. Hence, they are under-migrated. That's the famous hockey stick effect. Considering now the dipping reflector, you see that the situation is slightly different because all offsets see a strong effect of anisotropy. So when we neglect it, of course, the impact will be under-migration. Now, let's do the exercise of increasing the velocity. So now the velocity, vertical velocity is increased. If we further increase the vertical velocity, we end up with the flat gathers. Flat only for the flat reflectors, because if you look at the dipping reflector on the left, you see that we have not reached the correct flatness yet. This is, of course, explained by the rays, and we have to further increase the velocity if we want to get a flat common image gather for the dipping reflector. I like to say that instead of talking of long offset, we should talk of propagation directions when we discuss anisotropy. So in real life, tomography would be mainly constrained by flat reflectors or sub-flat reflectors, and that's the result we would get in terms of the pre-stack depth migration. We see that the gases are flat, the reflector is sharp, but at the wrong depth. And for the dipping reflector, it's not perfectly focused, but it's acceptable. And if we would drill a well, then of course things would be okay for the first layer, but we would have problems with the second layer. Let me zoom up this result and make the point that of course we are used to these vertical mistype, but insist a bit as well on the lateral mispositioning. So for instance, in this case, people might have thought that they are 100 meters from the fault, but they are in reality, they might be only 20 meters away from it. Quite important impact. More or less this is what happened in the real case that we saw earlier. So we can draw a few lessons already from this first exercise. If we migrate to the true vertical velocity coming, for instance, from the check shot survey or time depth curves or Marcus depths, we get the famous hockey sticks effect. However, we can find an isotropic migration velocity that in some ways flattens the gases, compensating for the presence of anisotropy. The corresponding image is reasonably sharp, but the anisotropic velocity globally overestimates velocities. This is related to the fact that epsilon is positive, and consequently flat reflectors are imaged too deep, and dipping reflectors are over-migrated and laterally mispositioned. Okay, so the next question is, could we have estimated vertical velocity epsilon and delta jointly with no well control? That leads us to the so-called Epsilon Scan. To test the idea, let's perform again a scan of vertical velocity in terms of the V0, V0 top, but now with various values of epsilon ranging from 0 to 20%. Note that for time being, I still assume delta equals 0. So that would be the result of isotropic case we just saw. But now, if I do my anisotropic scanning of epsilon, I got this result for 5%, this one for 10, this one for 15, and this one for 20. And you see that we get various results. This is what you call a non-uniqueness of the solutions if we have no well control, also called sometimes null space. But if we have well control, we can say, well, the correct result is on the right because that's the correct depth. Flatness is not perfect, mainly because we have an epsilon, not a true epsilon, by the way. This is basically because we have neglected delta so far. So a few lessons learned from this exercise. So firstly, the non-uniqueness of the VVert epsilon solutions. Secondly, that if we test various values of epsilon with the true vertical velocity coming either from the wells or from depths of markers, we get a solution, and that's what we saw in the previous real-life example. However, the value of epsilon that we find is not independent of delta. It depends on the dip of the reflectors, and basically is valid only around the wells where we have the calibration. So we need delta as well as epsilon as soon as there are propagations around 45 degrees with respect to the axis of symmetry. So how do we estimate delta? So for instance, if we assume that there is limited lateral velocity variations, we may think of pre-stack time migrations as behaving very much like pre-stack depth migrations. In this case, we may call famous equations introduced by Al-Khalifa, saying that the VNMO from pre-stack time is the vertical velocity time square root of 1 plus 2 delta. So we may have access to delta in this way. V vertical would come from borehole control. VNMO might come from the isotopic result that we just got earlier, and we may derive delta from that. We should realize that when we use these equations, we make the following assumptions. Firstly, that there are limited lateral variations of velocity and limited complexity of the subsurface. This would work for VTI anisotropy only. We neglect in some way vertical heterogeneity in the interval considered, and we get an effective or average delta, question mark whether this is a real propagation parameter. Instead of using the velocity, we may use the markers, so we can replace velocities by depths, and instead of using equations, let me look at it graphically. So that's a made-up example where that will be the result of seismic depth migration. Then you've got a well, as I said, it's necessary. Then in your wells, you define some key markers. then using seismic well tie in the vertical time domain, we find where the same markers are in the isotopically migrated depth image. And of course, the depths in the wells and the depths in the seismic image are different. So we may use the equations that we just discussed, the equations that we just presented before, and say, well, for that specific interval, that will be the average delta. And we can do that for various intervals at various depths. Okay, so we've now got delta using borehole information, and we can use the scanning technology that we discussed earlier to try to try and find the epsilon values that will flatten the gathers at the correct depths. Okay, so of course the values and of functions of interval delta and epsilon that we have estimated have been estimated at the wells. So we have to do some kind of clever geological interpretations to extend it from the well in an horizon consistent fashion. And of course we might have issues like, what do we do in this area which is different? So just in a nutshell, a classical flowchart would be start with isoprestack depth migrations, get the migrated image at the wrong depths, use the well control to estimate delta, do some scan to estimate epsilon. Alternatively, you might use prestack time migrations or other technologies which are around nowadays. Scan epsilon, extrapolate, include the axis of symmetry, and redo some kind of tomography to refine the vertical velocity, possibly the epsilon delta as well. This is a paper by Chang Li, so that will be the result of isotopic migration, that will be the result of VTI migration with delta, and that would be a field of delta as derived with the methodology which I briefly described. This gets me to the conclusions. Well, basically, we understand now that anisotropy is present almost everywhere. Not accounting for it leads to inaccurate images in terms of depths, which are systematically overestimated, and lateral positions of reflectors, including Thompson's parameters, vvert, epsilon delta, allows us to account for it and to get more accurate depth images. And these parameters, however, are not so easy to estimate, and the assessment of delta requires borehole control, and that's an important message. Of course, this presentation is not exhaustive. TTR is not discussed, and other strategies are used, including much more elaborate workflows, result of prestack time processing, inversion, rock physics constraints, and even constrained full waveform inversions nowadays. But building an anisotropy velocity model remains a very interpretative process. Thank you for your attention. You can like and share this video and leave your comments down below. And for more e-lectures, take a look at the e-lecture playlist.